So far, we have introduced three theories of bonding. The simplest that can be solved on a piece of paper is the Lewis structures. The followed, usually via CPR, complements Lewis structures very well, also can be solved on a piece of paper. And we just talked about the hybrid orbitals, or valence bond theory, maybe. It's valence bond theory, the way we described it, it was also fairly qualitative, mixing atomic orbitals to form hybrids so that we can predict the direction and the strength of the bond, and if there are any orbitals that do not participate in the combination, etc. This is fairly descriptive. However, valence bond theory can also be fairly mathematically charged with a lot of computations along with it. So it's not that different from the theory that we will introduce here, which is molecular orbital theory. And to understand molecular orbital theory, we need to understand, or at least try to review and remember, what atomic orbitals actually are. They are not just those clouds that we too often see on textbooks. They are actually waves of probability. And the waves of probability that the atomic orbitals are come from solving the Schrödinger equation. Simplified here, it looks like a wave equation, that it can actually get a little bit more complex if you work in the three directions of the space. You need to do a change of coordinates, and you need to factorize your overall atomic orbital into a radial and an angular component. The radial component gives you the size. This gives you the shape and orientation, etc. We'll not go into the mathematics of it, but the take-home message is that atomic orbitals are waves. Waves of what? Waves of probability. And when we describe the 3s orbitals, such as what you see on this picture, as that sphere of I don't know what, of electrons, that's always an approximation. We have to keep in mind that atomic orbitals, the way we understand them, are waves, concentric stationary waves of probability to find the electron, and that's as much as we can know about where the electron is. And as you can see here, the 1s, 2s, and 3s that on textbooks we usually see it as change in size, they actually change in nodes. The 2s has a node that is an area where there is zero probability to find the electron, so you can think of the 2s as two concentric spheres, and the 3s has two nodes, so it has three concentric spheres. So in any case, however, all of the s orbitals are waves of probability with concentric waves moving up and down. However, the excuse me, the p orbitals are not concentric. They actually, when on one side there is a large probability, on the other one there is a lower probability. Actually, the probability is the square of the function, but we will not go much into it. But they are still waves. They are still stationary waves, that is, they do not move with time, but the way we represent them here is always an approximation, because maybe these animated GIFs that you have on the left are a more accurate description of what the mathematical functions are about. Okay, and finally, the 3Ds. The 3Ds are more complex. They have more nodes, that is, more areas where there is zero probability to find the electron, but they are still waves. So that's what atomic orbitals are. Molecular orbital theory, and we are using operator notation, which you may not be familiar with. We have to solve the same wave equation that we used to solve atomic orbitals. It's just that it's now more complex. It's now more complex because we are going to find a wave of electrons for the entire molecule. And for example, if one of the simplest molecules, lithium hydride should be, so actually it should be a lithium hydride, so you usually put the more electronegative on the right. The overall wave of molecular orbital, and that's what a molecular orbital will be, a wave that gives you where the electron is in the entire molecule, will be a combination of atomic orbitals. So this is what molecular orbital theory and valence bond theory have in common. They all combine atomic orbitals to form an overall orbital. The only difference is that for valence bond theory, the atoms, the orbitals inside the same atom first combine to form a hybrid before combining with the others. However, in here, we use in the combination regardless of all of the orbitals, regardless if they belong to the hydrogen or the lithium. These do not form hybrids, no hybrid in here. It's just a different mathematical approximation, so that the overall molecular orbital is this wave of probability that is not located in a specific atom, will be in principle around all of the molecule. Okay, so what kind of combinations? The first take-home message is that if you combine two waves, two atomic orbitals, you can have a destructive and a constructive interference. So imagine that for the simplest of the molecule, H2, you combine the 1s of one hydrogen and you combine the 1s of the other. These are lone waves, and as you approach them, you can approach them in a way that they form constructive interference. We're talking about waves, so the interference can be constructive. That is, there will be some electron density between the atoms that is forming a bond, or they can form destructive interference. That is, you can combine these two atomic orbitals and make it in a such that they cancel each other out between the two atoms. There will be no bond. This is why the constructive interference is called a bonding molecular orbital. The destructive interference between the waves, it's called anti-bonding molecular orbital. And like hybrid orbitals, you will obtain as many molecular orbitals as atomic orbitals you have used in the combination. In this case, if you're using one s from one hydrogen, the other one s from the other hydrogen, you're using two atomic orbitals, you will obtain two molecular orbitals. In this case, one bonding, one anti-bonding. The way to label this molecular orbitals is using Greek letters. Typically, if the orbital has density along the axis, it's called an s orbital, so sigma. Sigma is the Greek letter for s, and if it's anti-bonding, it will have a star here. Okay, that's a little bit the take-home message or the basics of the molecular orbital theory. One would need to do calculations to actually look at these functions and see what they look like, but at least from the descriptive point of view, it already tells us that we will obtain two molecular orbitals. Okay, and we will draw the molecular orbital diagram as it's shown here. The bonding combination, this is the bonding molecular orbital, exemplified as sigma, and this is the anti-bonding, exemplified as sigma star. Star means anti-bonding, and well, the bonding combination will always be more stable than the orbitals combined, the atomic orbitals combined, and the anti-bonding combination will be more unstable, will have higher energy than the separated atomic orbitals. Okay, so if each of the hydrogen brings in one electron, we just need to fill in the two electrons. So we have the electronic configuration for H2 will be, if you will, this. This means that there is the sigma molecular orbital that contains two electrons. This is how we did it. We needed to place two electrons in our molecular orbital, and we start from the bottom, 1 and 2. That's it. We're done. We do not need to place any electron in the anti-bonding because we only had two electrons. Hopefully that makes some sense. We will practice more, but this is the basic strategy to form molecular orbital diagrams. And in here you have some simulations that may be useful to see how atomic orbitals combine to form different kinds of molecular orbitals.